class. Today we're going to analyze graphs of the quadratic function. And the objectives today are to find the vertex of a quadratic function using the vertex formula. Also find the axis of symmetry of the parabola and the maximum or minimum value of the function. We're going to graph quadratic functions using the vertex and intercepts of the quadratic function and also the concept of symmetry. And finally, we're going to solve applied problems involving maximum and minimum function values. Okay, well first what we need to do is talk about the definition of a quadratic function. A function f is quadratic if it can be written in the form f of x equals ax squared plus bx plus c, where this is considered to be the general form of the quadratic equation, and the coefficients a and b and the constant c are any real numbers with one exception. A cannot be equal to 0. That makes sense because if a was 0, we wouldn't have a quadratic term, a second degree term, and the function would be f of x equals bx plus c, which would be a linear function whose graph is a line. Well, we've already graphed quadratic functions when we studied the transformations of the basic functions. So let's recall a few things. First of all, the graph of a quadratic function is a parabola, and that's a U-shaped curve that can be oriented up or down. And the graph of every parabola evolves from the graph of the squaring function, the basic squaring function, f of x equals x squared, using transformations. Now when we graphed parabolas using transformation, we started with the quadratic function in standard form. This is standard form. F of x equals a times the quantity x minus h squared plus k. And remember that if a is greater than 0, the parabola opens up. If a is less than 0, it opens down. And hk are the coordinates of our vertex. Now if the parabola opens up, the vertex is at the very bottommost point of the graph, and k is a minimum because it's at the minimum height along the graph. If the parabola opens down, then k is a maximum value because it occurs at the place where the height is maximum. We also talked about symmetry when we graphed parabolas using transformations. We said that a parabola is symmetric about a vertical line that passes through the vertex point. And so here's our axis of symmetry for these parabolas. And what that means is that if we were to fold the parabola along this line, then one side would fall directly over the other side. The paths are exactly the same. Now because these lines, they're called axes of symmetry, are vertical, we know it has the equation x equals a constant, and it's going to be the x value of the vertex. So x equals h is the equation of the axis of symmetry. Okay, now let's review these few things here because they're extremely important and you need to memorize them. A parabola opens up if a is greater than 0, opens down if a is less than 0. hk is the vertex and x equals h is the axis of symmetry. And the value k is a minimum value if the parabola opens up, and it's a maximum value if the parabola opens down. Remember, they're very important. Memorize these ideas. In this class, instead of graphing quadratic functions in standard form, what we're going to do is we're going to start with the equation of the quadratic function in general form, f of x equals ax squared plus bx plus c. And we're going to determine the vertex and the intercepts, and we're going to use the concepts of symmetry to help us graph the parabola, graph the quadratic function. So let's look at the vertex formula. This is going to allow us to find the vertex of the parabola very easily. And the vertex formula says if we start with the equation of a quadratic function in general form, then we can use this formula to find the vertex of the parabola. This says that if we use the coefficients a and b and substitute them into this formula here, we can find and calculate the x value of the vertex. And the y value then of the vertex, the output value, we're going to find by substituting in this value we found into the function in place of x. And we're going to find the y value of the vertex. Okay, so when we graph quadratic functions starting with the general form, f of x equals ax squared plus bx plus c, we're going to graph it by using the vertex and intercepts of the quadratic function and the concept of symmetry. Okay, let's graph this quadratic function. We're going to graph f of x equals negative 3x squared minus 3x plus 1. And remember, the first thing we want to do is we want to find our vertex using the vertex formula. So the x value we're going to find by substituting into the formula, negative b over 2a. And a, of course, in this particular case is negative 3, and b is negative 3. So we have minus a negative 3 all over 2 times negative 3. And that's 3 over negative 6, or negative 1/2, is the x value of our vertex. And to find the output, or the y value of our vertex, we're going to have to put in negative 1/2 into our function. And that's going to give us a negative 3 times negative 1/2 squared minus 3 times negative 1/2 plus 1. And negative 1/2 squared is 1/4. 1/4 times negative 3 is negative 3/4. And then we have a negative 3 times a negative 1/2. That's a positive 3/2, but we need a common denominator of 4, so let's multiply 3/2 by 2 over 2, so we have plus 6/4. And 1 is 4 over 4. And now we can add and subtract our numerators. Negative 3 plus 6 is 3, plus 4 is 7. So we have 7/4. So we now know that our vertex is the ordered pair negative 1/2, 7/4. Or if you like, we can put it in decimal form. Negative 0.5, and 7/4 is 1 3/4, so that would be 1.75. Okay, now next thing we want to find, of course, is our intercepts. So let's find our x-intercept first. And remember, when we're finding the x-intercept, we want to find the places where the graph crosses the x-axis, and that's where the y value is 0. So that's what we're going to do. We're going to set y equal to 0. So we're going to have the rule negative 3x squared minus 3x plus 1. And we're going to set that equal to 0. Y is 0. And we could solve this if we wanted to using the quadratic formula, and we've done that several times in a previous section. So let's use the technology to help us arrive at those x-intercepts on the calculator. Go ahead to your y equals menu, and if you've got something in y1, clear it out, and we'll put our function into y1. We've got negative 3x squared minus 3x plus 1. Okay, and we're going to graph that in the Zoom decimal viewing window. So I'm going to go to the Zoom key and press that, and followed by number 4. 4 is decimal. And here's the graph of our function, our quadratic function. And what we want to do is we want to find decimal approximations for the x-intercept. Let's calculate or determine the x-intercept to the left of the origin first. So I'm going to go to the calculate menu, which is above the trace key. I'm going to hit the second key followed by the trace key. That'll give us the calculate menu. And we're going to find the zeros of the function. We want to find out where the y value is 0. So let's choose number 2. And what we have to do is we've got to feed in two separate x values that bound the x-intercept. So I'm using my left cursor key, and I'm going to go to the left of that x-intercept that I'm looking for. And because the function is increasing here, we've got to go below the x-axis. That's to the left. Let's enter that x value in. And we're going to use our right key, and we're going to go to the right, which is going to be above the x-axis. We're going to enter an x value in. The x-intercept is now bounded. We can move closer to it with our cursor key if we want to. And when we click enter, we see that the 0 is approximately negative 1.26 or negative 1.3. Okay, let's find this x-intercept to the right of the origin. So I'm going to run through the same process again. I'm going to go to the calculate menu. I'm going to choose number 2, 0. And another way that we can put in left and right bounds is just by actually entering in the values. And we notice that this x-intercept is between 0 and 1. So 0 is a left bound. I'll enter that in. And 1 is a right bound. I'll enter that in. And again, I'm going to use my left cursor key, and I'm going to get close to that x-intercept before I hit enter. And our second x-intercept is approximately 0.26 or about 0.3. Okay, so let's go back and let's finish our work for this problem. Okay, we found out that our x-intercepts are approximately negative 1.260. And the other x-intercept was about 0.26. And of course, y value is 0. So there's our x-intercepts. Let's find the y-intercept. Now the y-intercept is where the graph crosses the y-axis. And of course, any point along the y-axis has an x value of 0. And so we're going to set x equal to 0 in our function. And that's going to give us negative 3 times 0 squared minus 3 times 0 plus 1, or just 1. Now notice that that's the y value, that's the constant in our quadratic function, and that's going to always be the case. Okay, the y-intercept is always the constant term, because if you were going to replace x with 0 in any term that had a factor of x, that term would go to 0. And so, therefore, the y-intercept is always the constant term. And so our y-intercept is 0, 1. Okay, and we're ready to graph the function. So let's go ahead and graph this function. All right. Our vertex was negative 1/2, 7/4, and since all of these points are real close to our origin here, let's go ahead and use two divisions here as one unit. And so if I'm going to plot the point negative 1/2, 7/4, I'm going to go over to the first subdivision for negative 1/2, and 7/4 is about 1.1 3/4. So we're going to go up 1, that's 2 units, and 3/4, that would put us right here. There's our vertex. And our x-intercepts were approximately negative 1.3. That's located right about there. And our other x-intercept is 0.3, right about here. And we have a y-intercept of 0, 1. Remember, 2 of the divisions is 1 unit. And remember the axis of symmetry. We said that any parabola is symmetric about the vertical line that passes through the vertex point. And this, of course, is x equals negative 1/2. And what that means is if we go to a height of 1 on the graph, since if we move to the right a half a unit, we're on the graph. That means if we move from that axis of symmetry a half unit to the left, we're also on the graph. And let's join our points, and we have a nice sketch of our quadratic function. Okay, let's go to the best part of this lesson, everybody's favorite. Let's take a look at a application of a quadratic function. Yay, this is going to be fun. And let's take a look at an application that involves the height of a rocket. Okay, we've got a toy rocket that's launched with an initial velocity of 200 feet per second from the roof of a 50-foot building. Okay, and the function given here, s of t equals negative 16t squared plus 200t plus 50, gives us the height, which is represented by s, of the rocket t seconds after it has been launched. And of course, the height is going to be in feet. And we want to look at two things here. We want to determine the time at which the rocket reaches its maximum height and find the maximum height. And after how many seconds we want to determine after how many seconds the rocket's going to hit the ground. So let's first of all analyze this quadratic function. We know that it's a parabola, and we know that the parabola opens down, remember, because a is less than 0. And we know the y-intercept is 50. Remember, the constant is always the y-intercept. And so let's just give ourselves a rough sketch. And remember, we're going to launch this rocket off of a 50-foot building. So let's say here's our 50-foot building here, and we're at the top. Looking at this point right here. And if we launch that rocket, the actual path of the rocket just goes straight up and then comes back down once it loses its momentum. But we're talking about how does the height, which we refer to as s, how does the height in feet change as time in seconds passes? Well, what's going to happen is we're going to get a parabolic model, and the height of the rocket is going to keep increasing until it reaches its momentum or loses its momentum, and then it's going to fall back down to the earth. Okay, now, of course, the parabola continues on both sides, but the only part of the parabola that makes sense with this problem is this solid blue part. And if we find the vertex of this parabola, well, remember we said that's going to tell us the maximum y value, and the y values represent our height. The y values are the height in this particular case. So what we want to do is we want to find the vertex, because the x-coordinate of the vertex is going to tell us how long it's going to take the rocket to reach its maximum height. And the y value is going to tell us the actual height, time in seconds, height in feet. And then we want to look for this x-intercept to answer part B, because the rocket is going to hit the ground when its height is 0. All right, so let's go ahead and complete those two parts. Okay, remember that if we want to determine the time and it reaches its maximum height and the maximum height, we want to find the vertex. And the x-coordinate is going to tell us the time it takes to reach maximum height. And of course, the x-coordinate is the first coordinate, and in this particular case, the x-coordinate is time, so we're going to replace that x with t when we calculate that. And the y-coordinate, or in this case s, height, the y-coordinate of the vertex is going to give you the maximum height. So let's use what we just learned. Let's find the vertex by using the formula, vertex formula. And remember, the vertex formula says that x is equal to negative b over 2a, or in this case, let's change that to t because we're looking for time. And b is 200, so we have negative 200 over 2 times a, and a is negative 16. So we have negative 200 over negative 32, or we can reduce that. We're going to get 25 over 4. And that is equal to what? 6 1/4, so we have 6.25. All right, well, we know now that it's going to take, it takes 6.25 seconds to reach maximum height. But what is the maximum height? Again, we're going to use our technology to help us determine that value. So let's go over to the calculator and I'll show you how you can find the maximum of a quadratic function. Here, use the technology to help us determine the y-coordinate of the vertex. So again, let's go to the y equals menu and we'll clear out our last quadratic function. We don't need that. And we'll put in the function that we're working with. We've got negative 16x squared minus, or plus rather, 200x plus 50. Now remember, the variable is t in the formula, but the calculator works with the variable x. And I'm going to need to set my window by hand. So let's think about the fact that the x-intercepts are going to fall halfway in between, the vertex is going to fall halfway in between the x-intercepts. And we know that the x-coordinate of the vertex is 6.25. So I think what I'm going to do is I'm going to set my window for an x-min of negative 5 and an x-max of 15. Because maybe going another 6 units will get us to beyond that x-intercept. And I'm going to use a built-in feature of the calculator. I'm going to go to the zoom menu and I'm going to use my up arrow key, and notice that the very last feature is zoom fit. If I choose that, and since it's highlighted, all I have to do is hit enter. If I choose zoom fit, the calculator automatically takes the viewing window I set for the x values and adjusts the y values accordingly. And I think I'm going to go in and clean it up a bit because I'm going to try and find that maximum point, and it's at the very top of the screen, and if I leave it like that I might not be able to see what the coordinates are. So I'm going to change this to my y-min to, negative 50. We don't have to see below the x-axis very much. And I'm going to change my y value to, let's say 750. And that's just arbitrary. We'll put in a y scale of 50. And let's see what we got. All right, now just like we determined the x-intercepts before, there's a similar built-in feature on the calculator. We're going to go to the calculate menu, and this time we're going to pick maximum. We have a maximum point, and we have to do the same thing that we did before. We have to feed in a x value to the left and the right of that maximum point there. Okay, and I know that the x value of the vertex is 6.25, so I know that 5 would be to the left, and I know that 7 would be to the right. And then I'm going to use my left cursor, and I'm going to back up to about where the vertex is, and let's see what the maximum height is. Notice the maximum height is 675 feet. Okay, so we have our answer. Relatively painless, using the calculator. So let's go back and make our conclusion. Okay, so we found out that the maximum height is 675 feet. Now, one more thing here for this problem. Let's go ahead and find out how many seconds it will take for it to hit the ground. Okay, so again, remember that the height S is 0 when the rocket hits the ground. So we're going to take our formula and we're going to set it equal to 0. And that means that, of course, we want to find the x-intercept. And let's use the calculator to do that. Okay, let's go ahead and find that x-intercept on the calculator. Remember, we got our function in already. We've already looked at the graph. And there are two x-intercepts, but the one to the left of the y-axis is a part of the problem. We want to find the x-intercept on the right. And so we're going to go to the calculate menu. And we're going to choose 0 this time because we're working with the x-intercept. And let's see, I'm going to go close. I'm going to back up here. I'm going to change my viewing window because I need to see more of the x-axis. So I'm going to change my y-min to, negative 100. Okay, now I can see where my axis is when I go to the calculate menu and I pick 0. And I'm going to use my cursor and hold it down and trace till I get close to the x-intercept, to the left and above the x-axis. I'm going to enter in an x value. I'm going to move to the right of the x-intercept, below the x-axis, and hit enter. I'm going to back up. And we see that the x-intercept is, about 12.75. Now notice the y value is supposed to be 0. And you have to remember that the calculator works in decimal approximations. And 1 times 10 to the negative 10th, that scientific notation, is as close to 0 as you want to get. And so our x-intercept there is about 12.75. Okay, so we can conclude that the rocket hits the ground in approximately, we'll say in about 12.7 seconds. Okay, and that's our lesson for today. Make sure that you study all of these examples and work all the practice problems, and I'll see you next time.